Hey, so I sort of just wanted to make this video to provide some intuition for certain terms I didn't understand when I was trying to learn flow models. I'm still trying to learn them actually, but these are just some terms I didn't really understand in the beginning because when I started off, right, I knew what vectors were and I knew basic geometry, but I didn't really have a lot of intuition for what vector spaces were, and more importantly, I didn't really understand how this would tie back into the image space, the actual image, right? Like, I think I have this problem a lot where we're trying to dive deep into something, but then I just sort of end up getting lost on like what we're even trying to do, right? So sort of try to clear that up. So one of the first things I probably come across is this. This is the trajectory. Oops, sorry. This is the trajectory, right? So what is the trajectory, right? So what I initially mistook this for was just the position, right? By position I mean, so all right, let's start from here. So you have a 64x64 latent, right? So say you got this from your um, say you sample this from some Gaussian noise, right? So this is all initially just all garbage, right? So this is a 4096 d vector length vector, right? So this is a point in a in the 4096th dimension, right? Dimensional space. So and what we want to do in flow models or diffusion models is sort of turn this garbage into something that actually has meaning, right? Something that actually has meaning, right? That's what we're trying to do. Um, and we do that over time steps, right? So you must know about diffusion models. We do that over time steps, and so this vector will have different states at different time steps, right? Because it is moving to it is moving from noise to the actual image, right? So I hope that makes sense. And this is the sampling process in particular. We're not talking about training it, right? This is sampling. So it moves from this noisy state to its proper image state or whatever, right? So let's come back to trajectory. What is the trajectory? So the trajectory is I'm sorry. So say I have a 2D plane here and I have a point here, 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 right? The trajectory is essentially a function that sort of connects these points, right? So this is your x, uh, wait, this is your t, I'm sorry, and this is your x. So you have x at different time steps, right? So your trajectory is the function x of t, and you get the vector. I think this is probably better if I write this as v, right? The vector, right? This is the vector. Uh, so you get the vector at that time step, right? So this is what trajectory is. So it returns the vector. So you can think of this as the image vector at this time step. That is the trajectory. So it is a function, right? And this is what I was confused about. The trajectory is a function, right? But your vector is not a function, right? So this is, I think, an important distinction. So again, so if you sort of try to imagine this in the 4096th dimension, right? So this is what you probably saw it. So for this particular this thing, x at t0, you'd get v at 0, which would correspond to this noisy latent here, right? x at the trajectory at 1 would correspond to the vector at time step 1, which might be slightly. Alright, so another distinction here. So time steps that are actually from 0 to 1. So 1 would indicate the final stage. So so x at 1 would indicate v of 1, which is the fully denoised image, right? Image. Doing this with the mouse, so yeah, fully denoised image. So yeah, so this is the first this thing, right? So trajectory. This is what trajectory is, and the next term I think you'd need is the vector field. Oh, I'll just write it here. No, just alright. This is the alright. I'll decide now with the vector field. Alright. So vector field. Now what is a vector field? Right. So we all know what vectors are, right? Like this was a vector, like right? So a vector is something that has a direction and magnitude and is not restricted spatially to any place or whatever, right? Like that's the main distinction between a point and a vector, right? A vector is not a vector can be here, it can be here, right? So that's the main thing. So a vector field, let's get this. So again, let's use our V latent from before, right? 64x64. Let me just erase this. So let's use our 64x64 latent. The vector field is essentially, let me just, I think, so suppose you have a lot of points here, right? And just assume this to be some n-dimensional space and you have a lot of points here, right? And this is another important distinction here. So every point here corresponds to a vector, right? Every point is a latent like this. So because you are because you have a distribution, a data distribution, let's say this is the noisy distribution here. So every point here is a vector, which is represented as a point for, for convenience, but every point here is a vector, right? In the nth dimensional space. So if, and this is at t equals 0, right? And say at t equals, suppose 0.1, right? And these points scatter like this, right? So they move to hopefully uh, form our destination distribution. So when this happens, your vectors change, right? Naturally they change, right? So what a vector field is saying is at any time step t, the vector field will give you in what direction these points are moving in. So essentially it's their derivative, right? So at, so if we assume this movement here from t0 to t0.1, and if I were to draw the vector field at this point, right, this point moves here, so a vector field for that point would be like this. The vector field for this point would be like this. The vector field for this point would be like this. So get the idea, right? So it shows the direction, every point, every latent, every image. Every point is an image. So because every vector is a uh, uh, this this corresponds to a latent image. So every point corresponds to a latent image. So it shows you how this point moves, how these images, these latent images, these latent representations of images move at this time step, right? So that is all you need to know for now for vector fields, right? So, and this is exactly what we're trying to learn. So, in our flow model, right? This is what we're trying to learn. We're trying to learn to, um, we're trying to learn this vector field, right? Like, um, because we want to move from here to this, the final distribution like this, say. So how do the vector fields look at each time step so that we can follow these directions, right? I hope that makes a little sense. I'm not, it's my first time trying to explain something to others, but yeah. Right, so that was the vector field, and I'm not, this is the thing not noted by you. I'm not really going deep into this notation right now because I think I might make another video after I've sort of um, mastered this concept or whatever, but yeah, this is the vector field. And finally, how do we get the vector field? Right, how do we get the vector field? So the vector, so if you uh, if you studied physics or graphics or whatever, computer graphics or whatever, right? Like if you have a hold over linear algebra, so this you'd get if you differentiate, right? A derivative, you need to find the derivative. So for every point again represents the latent image, right? For every latent image, you need to find its rate of change, right? And this is the ODE, the ordinary differential equation. This is what guides the flow equation. So diffusion models have a SDE, so that is a stochastic differential equation where they inject Gaussian noise as well into the equation, but I think that's another topic altogether. I think there's more complexities there because you can't really differentiate Brownian noise and all that. So which is essentially Gaussian noise. So yeah, so first this is an ODE. So basically, I need to differentiate. I need to somehow get the speeds or the velocities of every every vector here, right? Every vector to get the vector field, right? So if I d by dt of this equation, trajectory of t, right? So again, what does this mean? This will give me the vector at t, right? It's essentially vt, which is what we're trying to differentiate. You will get u, which is the vector field of the trajectory, right? And this, uh, I suppose how you would calculate is basically you could like try to calculate the slopes between these, and by slope I mean set the limit to zero and do that, but we can use solvers I suppose for this, but yeah. This is what we're trying to learn essentially. This is what we're trying to learn. Um, right. So this is how we get the vector field, right? And yeah, so this is how we get the vector field. And again, so suppose this is all I wanted to like give you intuition for. Again, this is a very basic video, and I'd suggest checking out MIT's course of flow and diffusion models. I think flow diffusion. It came out in March of this year, so I actually sort of made this video because I just wanted to sort of make this video if someone was struggling with these terms or trying to uh, struggling with the bigger picture if I relate it to latents and images. So I think after this, I think you'll be more prepared to sort of understand the concepts there.